So let me start by telling you what a cylindrical shell is, what it looks like. So cylindrical shell is essentially an object. I'm going to do my best to draw this picture for you. It's a cylinder, a circular cylinder. So, but it's a very thin circular cylinder. So inside of this, you're going to have a big hole. Inside the middle, okay? So think of maybe like a pipe. A pipe has a big hole in the middle, and it's very thin around the rim of it, okay? So there's a lot going on with this. It's kind of similar to when we had the washer, because we have an inside cylinder and an outside cylinder. With a washer, we have an inside circle, outside circle. So I have two radiuses going on. I'm going to have R1, which is going to be my inner radius of the one with the hole, the radius of the hole. So this is R1. R2 is your outer radius. So it would be all the way out to the outside. That's R2. And then I also have height, which is the height of this shell, of the cylinder H. Okay, and I need to calculate the volume of this cylindrical shell. So how do we handle calculating volumes when I have holes in the middle? I pretend like it's filled in, calculate that volume, and then subtract the filled in volume, okay? So to find volume here of this cylindrical shell, which I'm going to call V, it's V2 minus V1. So I'm using V1 for the inner volume and V2 for the outer volume. But each one of these things, V1 and V2, the outer part is a cylinder, circular cylinder. The inner part is also a cylinder. And we talked about the volume of a cylinder. What's the formula for the volume of a circular cylinder? Pi r squared times h. The area of your bottom times the height. Okay? All right, so I can use that formula here. This is pi. I'm using the outer volume, so it's R2. That's my radius for the outer, times h minus pi, or R2 squared, R1 squared times h. These things have a lot in common though, right? These two terms. If I look, they both have a pi and they both have an h. So I'm going to factor those out. I'm going to factor pi R2 squared minus R1 squared. And I'm going to factor the h out on the backside. Okay. This is a difference of squares. R2 squared minus R1 squared, which you can factor. Right? If I asked you to factor like x squared minus 4, how would you factor that? Yeah, plus and minus, right? They're exactly the same, but I have a plus and a minus. So we're going to use that same idea here. I can factor this as pi R2 plus R1, R2 minus R1. Okay. All right. Okay. So I'm going to manipulate this equation so it looks nice. I know this is going to be a little weird. We're just trying to come up with a nice formula. So I'm going to put in a 2 here, but then I'm going to divide by 2, so I didn't change anything. And I'm going to move this h here. Okay. All right. So R2 minus R1, let's think about this in context of our picture up there. R2 minus R1, that's really how thick this shell is, right? I take my bigger radius, subtract my smaller radius. I'm just getting the thickness of this shell. So I'm going to relabel R2 minus R1. I'm going to call that delta R, and this is going to represent the thickness of our shell. Our cylindrical shell. Yep.
Where did you get this 2 from?
Okay, so I just inserted in a 2 and then divided by 2, so I didn't change anything because they cancel, right, and give me the same thing. It's also I can write this in a nice way, okay? It just happens. I just did it so that I'll get this 2 pi here, and now I'm going to do something with this other term here. Okay, R1 plus R2 over 2, that's an average, right, of my 2 radiuses. So remember, we're thinking about, let me go back up to the picture. This is, I said, a very thin cylindrical shell. It's a very thin rim. So really those 2 numbers, they're pretty close to the same thing, R1 and R2. So I'm just going to relabel that an R. Okay, a single radius. So relabeling, I'm going to call R, R2 plus R1 over 2. And the idea is it's because this cylindrical shell, it's very thin. So really R1 and R2 are almost the same thing. So if I plug these new labels in, my volume becomes 2 pi, and then this thing, this average is now replaced with R, H delta R. And that's our volume formula right here for that cylindrical shell. So the reason why, now I'm going to tell you that I put that 2 in there, when you see this formula, you can break it up and think about it like this. 2 pi r, that's the formula for circumference of a circle. So and then this is h is height, and this delta r we said was thickness. So you should think of this as saying that the volume is equal to circumference times height times thickness. So I put that 2 in there so we could think in terms of circumference. All right. Okay, so now we know how cylindrical shells work. And the idea is we're going to use them in our solid. We're going to break up our region into these cylindrical shells. So let me tell you how that works. We're about to start doing problems, I promise. Okay, so let's say I have a solid S. and I'll draw a picture in just a second, obtained by rotating the region bounded by some curve, y equals f of x. And here I am assuming that this function f of x is going to be not negative. Y equals 0, x equals a, and x equals b. And one of these two numbers is bigger than the other, so I'm assuming b is bigger than a, and they're both positive about the y-axis. So the picture is that I'm looking between a and b for x. My function is positive, so it's in the first quadrant here. So let's say my function f of x looks like this, and I'm only looking between a and b. I want to rotate around the y-axis. Now, the way we did volume before is we would take our strips perpendicular. We took them horizontal, like we did at the very beginning. Now you're going to take them parallel. You're going to take them vertical. Okay, so my strips now are going to be up and down. And what you're doing is you're taking this thin strip and you're rotating it around, and you're getting that thin pipe or tube, if you want. A very thin cylindrical shell is what you get when you rotate this around. All right. What's nice now is that because our strips are vertical, I have a top bottom, which means I'm going to integrate in terms of x. Okay. So you get to integrate in terms of x. And the formula is going to be, I need to figure out radius. The radius of the strip from my rotation line. It's that distance there, which is x. And I'm integrating in terms of x, so the radius is just going to be x. And the height of my strip comes from how tall my function is. So the height is my function f of x. So maybe I'll label it here. This is my height. Once you know the radius and the height, we just need to use our formula. So the volume, we said 2 pi r, which is now x, times my height, times my thickness, which is dx. It's very thin. And my bounds are going to be from A to B. Okay? So this is your formula for finding the volume if you're rotating about the y-axis.